chiral dynamos without initial chiral imbalance.
Okay,
Using
can
the
you see my
pencil.
screen?
Yes.
Okay, great.
Jennifer, and we are recording it, as you already know.
Okay, thanks a lot. So yeah, good morning everyone, or good afternoon, and thanks a lot for Piali and the local organizers for making this happening. So it's great to contribute here and to participate. I will present today a paper that came out earlier this year with my co-authors Igor Gorevsky and Axel Brandenburg. So the topic of the paper is chiral dynamos without initial chiral imbalance. Let me start with a quick overview of the topic. So I'm moving now away from the sun to the larger scales of our universe. So this is regarding cosmological magnetic fields, and what I show on this slide is what we know about the history of the entire universe, or what modern cosmology predicts for or tells us about the history of the universe. And time starts here at the very left with the Big Bang. Then we had a phase of inflation where the universe expanded very rapidly. Even after inflation, the universe continued to expand and therefore cooled down, and therefore this primordial plasma cooled down more and more until 400,000 years later, when it cooled down enough so that ions and electrons recombined and the universe became neutral, releasing the cosmic microwave background. And then at later times, the universe continued to expand, but eventually gravity took over and cosmic structures formed. So galaxy clusters, galaxies, and this large scale cosmic web. And we are here on the right-hand side for almost 14 billion years after the Big Bang. Now, this is the picture we have in mind in cosmology, but of course we need to test our ideas, and therefore traditionally one uses photons, so we collect lights from different sources, and depending on how strong these light sources are, we can only probe a certain distance of the universe or a certain age of the universe. So if we look at individual stars, we get up to here. We look at entire galaxies, we can observe a larger fraction of the cosmic history. And the furthest we can look by using light is given by the cosmic microwave background, which you see here in this picture. We cannot look beyond the time of the release of the cosmic microwave background, because before that time, the universe was composed of an optically thick plasma. So there were photons, but they were scattered all the time. And therefore, you can consider this as a very dense fog. We can simply not look beyond that with light. But there are other proposals that allow us to probe the universe when it was much, much younger. And one of the methods that we can in principle use are observing primordial magnetic fields or gravitational waves from the early universe. So we've already heard about gravitational waves yesterday from Alberto, and I think there's another discussion after the break on that. So I will not talk about gravitational waves at all. I will focus on these primordial magnetic fields and how we can use them to learn something about what happened a second after the Big Bang. So this is the outline of my talk. I will give you a very brief introduction to cosmological magnetic fields. I will talk about MHD in the early universe in general, and then I will come to my main topic, which is chiral dynamo instabilities. So already yesterday we got a nice overview about how magnetic fields can be generated in the very early universe. I call them seed magnetic fields here, and there are different different mechanisms that can generate magnetic fields. For instance, there's inflation, and certain inflation theories predict the production of a magnetic field. You see there's a large variety of strengths there. So the theories are not very well constrained. Same is true for these cosmological phase transitions, especially if they are of first order. It's possible to generate magnetic fields during these events. After the generation, basically we have to deal with the evolution of these primordial magnetic fields. And as you know, the evolution of the magnetic field in the plasma is determined by this dynamical variable. So we have to follow the evolution of B. But that is coupled to the evolution of the velocity field or the density field. And we also need to have an equation of state. Now, in this very high energy, high temperature plasma, in principle, we have to solve the fully general relativistic MHD equations. But if we rescale our quantities in a smart way, then we can, instead of solving the fully relativistic MHD equations, we can solve just the regular MHD equations under some conditions. So we need a flat universe, we need a radiation-dominated universe, but then we can rescale all our quantities and arrive at like the MHD equations that we know. And this was, of course, a very important contribution to this field by Axel a while ago. So we will solve the MHD equations, keeping in mind that we talk about co-moving quantities and conformal times. So yeah, this decaying MHD turbulence, so this evolution of these primordial magnetic fields comes to an end when we reach the time of recombination. So then the plasma suddenly transitioned into a neutral state. And after that, basically, we just have a passive evolution of this primordial magnetic field. So it's just frozen into the Hubble expansion of space. And not much interesting evolution is happening until this cosmological structure formation sets in these densest regions of the universe. As you know, during structure formation, there are many possible ways to generate turbulence, like by accretion of material, by supernova explosions, and additionally, we have large-scale rotation of objects, and all of these mechanisms, they allow for dynamo activity in the dense regions of the universe. So in the dense regions, the magnetic field undergoes a very dramatic evolution at late stages, and eventually we end up with the modern magnetic fields that we observe in today's universe, in galaxies or even in galaxy clusters. So this is the evolution of the field in this nonlinear structure formation. But as you see, maybe I should go back, as you see here in this modern universe, we have the dense regions, but there are also these large empty regions that are called cosmic voids. And if we find magnetic fields in these cosmic voids, they are basically fossils of the primordial magnetic field that has been generated in the very early universe, because there's no way that they can evolve very strongly. So these are really very precious pieces of information that allow us to learn something from what happened shortly after the Big Bang. Now, unfortunately, it's not very easy to detect magnetic fields in cosmic voids, but there are a bunch of observational constraints on those. So what you see in this plot is a summary of all of the observational constraints on magnetic fields in voids. So here's plotted the co-moving magnetic field strength versus the correlation length of the magnetic field. And all of these gray and dark blue regions, they are excluded by observations. So the magnetic field in void should be somewhere in this wide region, and I don't go into details at this point. But this gives us a very useful constraint on the magnetic field and on early universe physics. So it's important to keep in mind that everything that happened in the very early universe happened on rather small spatial scales, because the universe was just much, much smaller, or the Hubble horizon rather was much, much smaller shortly after the Big Bang. So the magnetic field has been generated on very small length scales in the early universe. And I just, as a sketch, put here two different initial magnetic fields, seed magnetic fields. But of course, they evolved during this plasma state of the early universe. Today we would expect those magnetic fields to be somewhere in this region. So I just also, as a sketch, put three different final values of the magnetic field that we would observe today in voids there. And depending on how the evolution goes, we end up at three different final points in this diagram here. And based on our observations, we can exclude this final A scenario. We can also exclude the final C. So in that case, only the magnetic field that generates this final B condition would be allowed by observations. And this is how one potentially can probe early universe physics. Okay, let me talk a bit about MHD in the early universe. So let me start with the classical MHD. So as you know, in MHD, MHD is based on electric currents, and normally we have the ohmic current that we can combine with Maxwell equations in order to derive the induction equation for the magnetic field, which I wrote down here. And the induction equation has a very interesting property, and that is that it tells you that magnetic helicity is a conserved quantity, at least in the limit of vanishing eta. The global magnetic, the mean magnetic helicity is a conserved quantity. So I just, as a sketch, added here these ropes here. So the magnetic helicity is, of course, a topological property of the magnetic field, describing how it is, how it's wrapped around itself. And this magnetic helicity conservation has a very important consequence for the early universe. So first of all, this limit eta goes to 0 is very well satisfied in the early universe, because it's a highly conducting plasma. And then using this conservation law and using an approximation of magnetic helicity like that, so we can just write magnetic helicity as correlation length times b squared roughly, and then this allows us to predict the evolution of the magnetic field. So if it decays, if B decays, in order to conserve magnetic helicity, the correlation length needs to increase, which is known as the inverse cascade in MHD. This inverse cascade then allows us to really prescribe the evolution of the magnetic field in such a parameter plot. So here I have put the initial value of the magnetic field, maybe generated through a phase transition here. And then if we have a helical magnetic field, we can exactly say how the magnetic field evolves and where it ends up in this parameter space, which is down here. And even, by the way, in for non-helical magnetic fields, we can predict, or it's possible to predict the evolution of the field, so there's also an inverse cascade, as Tina Kaniashvili and Axel and others have shown, but it's less efficient, so we end up at a different place in this parameter plot. Yes, so this is the picture using classical MHD. But in fact, the energies in the early universe were extremely high, if you go back to a second after the Big Bang. And these high energies, they allow for quantum effects to contribute to electric currents. So if we go to these very high energies, the electric current in the system is not only the ohmic current, but there are some quantum effects that lead to additional electric currents. And one of these quantum effects is the so-called chiral magnetic effect. Very briefly, so this is related to fermions in the early universe, which can be either left-handed or right-handed. And if you put these fermions in a magnetic field, then the spins of fermions will align. So the right-handed ones will move upwards, while the left-handed ones move downwards. And if you have more right-handed than left-handed fermions, there will be a net current along the magnetic field. This current is related to this asymmetry of number densities, or rather we talk more about chemical potentials, and the chiral chemical potential is just like the difference between left and right-handed chemical potentials of fermions. So the net current that we expect from this effect is proportional to that mu5 times b. If we have this additional current, then we again can combine this electric currents with the Maxwell equations, and that leads to a modified induction equation, which I wrote down here. So basically, in comparison to classical MHD, we have one additional term here at the end. And this term is related to this chiral chemical potential, mu5. And mu5 itself also has an evolution equation, which is really founded in the quantum effect. So mu5 is coupled again to B. So MHD gets much more complicated taking into account these chiral effects. And just one of the most remarkable consequences of these additional terms and equations is that there is also a conservation law, but magnetic helicity in chiral MHD is not conserved anymore, but rather the sum of magnetic helicity and what I call often like simply chirality, so this chiral chemical potential multiplied by some constants, the sum of these two quantities is conserved. So we can, in chiral MHD, exchange this chiral symmetry for magnetic helicity or vice versa, and that makes the dynamics of a chiral plasma much more complicated. So if we just look at this chiral induction equation, you've seen it before, there's this additional new term in the end related to the mu5, and if you work on mean field dynamo theory, you may realize that this term looks a bit like the alpha term in the mean field induction equation, and then you directly notice, oh, that's an instability in the magnetic field, and this instability is, however, not related to turbulence or to any mean field effects. This instability also occurs in the total induction equation, and we can solve this with an exponential ansatz and find the growth rate of this instability, which the growth rate is related to the value of this chiral chemical potential, and the larger the chiral chemical potential, the smaller the spatial scale on which this instability occurs. And this is something that has been already realized a rather long time ago, that this presence of the mu5 leads to an instability. So it has also been realized what stops this instability, and well, basically we can look at the conservation law in chiral MHD, which tells us that this quantity is conserved. So if we have a mu5 in the system, we can exchange all of that for magnetic helicity, and then the dynamics comes to an end. So that was rather clear for a long time. However, if we look at the full set of equations, there's of course also a velocity field. So we have this u here in the induction equation, and u evolves according to the Navier-Stokes equation. And in the Navier-Stokes equation, we do have the Lorentz force acting. So if we generate a strong magnetic field, we also drive turbulence, and that makes things much more complicated. And therefore, we started using the Pensacode to solve these equations numerically and to follow the nonlinear dynamics of the system. So Chiral MHD is a special module of the Pensacode. You find it in the special folder. It's called Chiral MHD, and it can be switched on if you want to solve this full set of Chiral MHD equations. I already gave a presentation on that 2 years ago at the Pensacode user meeting, so I don't go into details, but rather show you some results of this Chiral MHD simulations. So starting here with a simple setup, just for comparison, if we take a periodic box in the Pensacode and we put in a weak magnetic seed field, and if we don't drive turbulence, then the magnetic field will just decay in classical MHD. But if we solve the Chiral MHD equations, if we insert a uniform mu5 in the box, then we see that the magnetic field grows exponentially until it saturates due to the chiral conservation law. And you see here at saturation, the mu5 itself decreases. So the conserved quantity is conserved in our simulation. So this is the case if we use rather large values of viscosity and in the system. But if we lower that, and if we allow turbulence to evolve, if we allow for Reynolds numbers to grow to high values, we see a slightly different, or we see a different picture. So in the turbulent case, we do still see this initial exponential amplification at the rate that we expect from our pen and paper solutions, but at late times, once turbulence has developed, the growth rate of the magnetic field changes. If we look into snapshots of this run, so initially we just normally have a random noise magnetic field, then we see that small scale chiral instability that generates the magnetic field at the we can see that the magnetic field rather is evolving on larger spatial scales. And this is something that we have discussed in detail in this paper led by Igor Gorchevsky. So in fact, at late times when there's enough turbulence in the system, there are some mean field effects that lead to a large scale dynamo instability in this chiral MHD. Today, I want to extend that picture a little bit. I think I don't have too much time left. I will try to be brief. So this is the case that we have studied during the past years since 2017. We always considered a very uniform chiral chemical potential in the entire universe, basically. So in the most extreme case, we only have right-handed fermions in the system. So we studied cases where this mean chiral chemical potential at the beginning was finite, and that led to this chiral dynamo instability. What we recently did in our new paper is we looked at a scenario where on average in the entire universe, the mean chiral chemical potential was 0, but there were fluctuations in mu5. So locally, if you look at local spots in the universe, there are regions where the chiral chemical potential is non-zero. And that is a situation that can be more easily realized in the early universe, so it does not require any very specific generation mechanisms. So it's much more realistic, and it's rather unavoidable in a sense. So what we did in our first tests with the pencil code is, again, we use a very weak magnetic seed field, and we use fluctuations of mu5 in our box at time 0, but the average of mu5 in the entire box was 0. And I show you a couple of toy models here. Just for comparison, I show you a case in red here where really we use in the entire box the mu5 that was like constant and uniform. So this is mu5 as a function of x, now as a 1D case here. And yeah, this is the scenario, the evolution scenario for mu5 and b, as we have seen it in all of our previous studies. So exponential increase of b, and eventually at saturation, mu5 drops to small values, and the magnetic field saturates. But now we can set in our box some fluctuations of mu5, for instance, a sine wave, which on average leads to a vanishing mu5, but locally there can be large values of mu5. And you see here the comparison of the time evolution. So we again see an exponential increase. The growth rate is a bit smaller, but we see a rather similar picture in this case. But if we increase the frequency of that, like the spatial frequency of that sine wave here in our initial condition, the growth rate gets smaller and smaller, and eventually, if our sine wave is, if mu5 is fluctuating too much, there's no amplification of the magnetic field anymore in the system. So we have looked at this typical characteristic scales in the system, and we could find that if the instability scale of this chiral dynamo is much smaller than the scale on which mu5 itself is correlated, we did not see any dynamo instabilities anymore. So this was just a toy model for which we used the pencil code, but we also looked into slightly more realistic scenarios where we just put random fluctuations in the box with certain spectra and just let it evolve. And I'll show you here a quick video of the magnetic field evolution in such a scenario. So we see that where originally the mu5 fluctuations were the largest, there in these regions the magnetic field is growing the fastest, and at later times you see that the magnetic field also develops in other regions, and it reaches larger and larger spatial scales. So we have analyzed such kind of simulations a lot. I can give you more quantitative evaluation of that, but very briefly, maybe we can look at this plot. So I plotted the magnetic field strength as a function of time here, and I looked in particular at the fluctuations of B and on some kind of average of the magnetic field, and you can see how these two fields evolve there. And in particular, if once the Reynolds numbers reach higher values in our system, the growth rate changes very much, and you see that in this growth rate plot here in the bottom. And we were mostly interested then at these late times when turbulence has developed in these runs, because we could find that the magnetic field continued to grow, and we were interested in whether there are some mean field effects in these simulations. And especially here at these late times. So we were interested in whether such random fluctuations in mu5 could also generate a large-scale magnetic field. And yeah, again, looking at time, I think I should hurry up. We could find that by looking at the different alpha components, in particular the magnetic alpha effect, explained very well this growth rate of the magnetic field at late times. So basically in our new work, we could show that these chiral dynamo instabilities occur also if there are only fluctuations in the chiral chemical potential in the early universe, if these fluctuations are correlated on rather large scales. And in these cases, we can also generate mean fields, and even mean field dynamos exist that can be described by a magnetic alpha effect. Just 1 minute of a current project. So in principle, it's also possible to generate a chiral chemical potential from 0. So if we start with this vanishing chiral chemical potential and also vanishing fluctuations, it's possible to generate nevertheless a mu5 in the system if there are chiral magnetic waves. So far I've only talked about this chiral magnetic effect, but there are further quantum effects from the standard model of particles that allow for more complex dynamics, and one of these are these chiral magnetic waves, which describe the gap between the chiral chemical potential and the chemical potential, which is just the sum of left and right-handed fermions. And including these extensions in our model, there are there's this coupling between mu, so the chemical potential, and the chiral chemical potential. So if we have some gradients in the chemical potential, we can generate a mu5. So we have a source term for mu5, and that can then lead to a dynamo instability in turn. So we have run some preliminary simulations to show that this works, but I think I'm running out of time. So let me just come to my conclusions. So the evolution of these primordial magnetic fields is coupled to the evolution of this chiral asymmetry. So we have to use chiral MHD if we want to describe really the first second of the primordial plasma. And this is very different from classical MHD. And in particular, we have shown using the pencil code that chiral mean field instabilities also exist even if there's no initial chiral asymmetry in the early universe. And our final goal of all of these studies is, of course, to use these results of the evolution of primordial magnetic fields in order to distinguish between different early universe theories as summarized in this plot. So if you're interested in more details, there's our recent paper, and you can also ask me questions on Slack or right now. So thank you.
Yeah, thank you, Jennifer, for a very clear talk. Let me check if there are, we can have, quick question. Oh, there are several. So there is one by Ram Kishore Sharma.
Mm-hmm.
Hi, am I audible?
Yes.
Thank you, Jennifer, for this very interesting talk. I have just very quick question, regarding these fluctuations of mu5. So for a realistic case, you took a spectrum like K-2 for the mu5.
Yes, this is
and
one example.
It seems, it's one example. Okay. And it seems it will have more power on the large scales.
Yes.
And so do you have large magnetic fields generation in this case, or? And can this be realized, or what may be the, is this a physical or realistic one spectrum, or?
That is a good question. We don't know very well.
Okay.
But what I can tell you is that we tested different scenarios. So we tested a couple of very steep spectra. So k to the -2, k to the -1, also k to the -3. And the steeper the spectrum, the better it is for the generation of a large-scale magnetic field. We also tested positive slopes of the spectrum, and there it becomes really, really difficult to generate enough mean mu5 in the system so that the dynamo instability is efficient. So it is a lot connected to scale separation. So if mu5 is correlated on smaller and smaller spatial scales, it is more and more difficult for the chiral dynamo instability to develop. So we played with the spectra a lot, and there are a lot of examples in the paper. Yeah.